Hello everyone, good morning. It's another lovely Wednesday morning. I hope you've been having a lovely week. So today we're going to be dealing with further mathematics and we're talking about a new topic. But before that, I want us to just look at our mental matrix for today. Okay, this is a simple one, very simple one actually. Compensation. Now, what's it all about? It's more of addition and subtraction. So you have numbers that you want to add and subtract, and then you want to find a way to make it easier. Like I've always said, mental matrix are not. You don't have to pick every particular trick. If you like some, you take them. If you don't like some, you leave them. So 563 plus 652. Now, to make our work easy, we can try to round this, make these values round figures. Now make our addition easier. Okay, so we can round 563 to 560. That's, we removed 3, right? And then we can round 652 to 650. That's, we removed 2. Now if we do that, we'll be left with 560 plus 650, which is actually easier to add in your head. So 560 plus 650, oh, 1210, right? It's easier to add in your head. And then after doing that, you now have to bring back the figures that you removed. So you add the 3 and the 2 that you removed previously. Okay? So then you have 1210 plus 5. That gives us 1215. So all these need to be done as quickly as possible. So the only way you can perfect something like this is with practice. So it will help you, if you decide to use it, it will help you to do addition faster. You can also apply the same thing to subtraction questions. Okay, so what if you have 895 minus 549? But for subtraction, you may not need to round the first number, you may just need to round the one that is being subtracted. So you may just need to make it a round figure. So 549 can just be made, you can round it to 550. So 550. Then the subtraction is easy because 895 minus 550 just gives you 345. But you need to remember that you have to add the one that you added to 549. You need to add it back to your answer. So that gives you 345 plus 1, which is 346. So this concept is called compensation. Okay, so you can try to apply it to your matrix if you and to your math calculations if you want to. It might be helpful for you. Okay, so that's that for our segment on mental matrix today. Okay, so we're talking about a topic in further maths called partial fractions. Partial fractions. We've all treated fractions at one point or another in our in our lives, in our study of mathematics and further mathematics. So we all know that, okay, we have different types of fractions. So for example, when you have 1 over 2 plus, 5 over 6, and you add that together to get another fraction, that's just the concept of fractions. You're familiar with that. Okay, but now, let's talk about partial fractions and compound fractions. Let's define it and see what this means. Now, what would you do if you're asked to combine algebraic fractions like this? You have to combine algebraic fractions like this. Okay, your first thought is that we are going to find the LCM. Yes, we're going to find the LCM of the denominators and then use that to combine the fractions together. So we're going to have something like this: x plus 1, x plus 5 as our denominator now, the new denominator, and then we do 3 in x plus 1 in x plus 1, x plus 5 is x plus 5. So we have 3 into x plus 5 plus 4 into x plus 1. So the left-hand side, the two fractions on the left-hand side are called partial fractions. Now, if we resolve the right-hand side, if we simplify the right-hand side, we will obtain what we call a compound fraction. So a compound fraction is simply a combination of two partial fractions. So let's try to resolve the right-hand side, and by opening the brackets, in the numerators, in the brackets in the numerator rather. So we have 3 into x plus 5 gives us 3x plus 15, and 4 into x plus 1 gives us 4x plus 4. If we collect like terms, we have 3x plus 4x plus 4 plus 15. And then we have 7x plus 19 over x plus 1 into x plus 5. Like we said, this fraction is called a compound fraction. So the concept of partial fractions is that you would be given a compound fraction and you would be asked to resolve the said fraction into as many partial fractions as it can obtain. Okay, so that's what we're going to be discussing now. But before that, let's talk about the methods that you can use to split partial fractions. Okay, we're going to talk about the methods that you can use to split partial fractions. So types of partial fractions, we can have partial fractions, or let me say, types of partial fractions that we can resolve into depend on the type of compound fraction that you're given. Okay, the type of partial fraction you will be resolving into depends on the type of compound fraction that you're given. So when you have a compound fraction that it has a non-repeated linear factor in its denominator, how do you resolve it into partial fractions? Okay, so let me just show you what I'm saying. So for example, the denominators of the fraction you're given is linear. For example, it's in the form ax plus b. How do you resolve it? Let's look at this. So you have 7x plus 19 over x plus 1 into x plus 5. Look at the denominators. That's what we looked at before. The denominators are x plus 1, x plus 5. They are both linear. So if we're going to resolve this into partial fractions, we're just going to assume a letter as the numerator, either A or B or C or D. We're just going to assume a letter as the denominator because, as the numerator rather, because the denominators are linear. Okay, take note of that. We're just going to assume a letter as the numerator for each partial fraction. Another example, you can see the denominator for that next one is x plus 4 into x squared minus 9. At first glance, it doesn't look linear, but you notice that x squared minus 9 can be resolved into x minus 3, x plus 3. That's we have difference of two squares there, x squared minus 9. So it can be resolved into x minus 3, x plus 3. So it's still linear. The factors in the denominator are still linear. So if we're going to also resolve this into partial fractions, we would use a single letter as the numerator of each partial fraction. Now also take note that the number of partial fractions depends on the number of linear factors in the denominator. So for example, the first one, 7x plus 19 over x plus 1, x plus 5 will have 2 partial fractions. The second one will have 3 partial fractions since it has 3 factors in the denominator. Okay? So enough of all the talking. Let's look at a real example of these fractions now. Let's just solve the first one so we can confirm our answer is correct. Since we combine partial fractions to get 7x plus 19, let's also split it back and see. So let's talk about the methods. We can use the cover-up method. That's the first one. Cover-up method is easy, but sometimes you cannot use it for big fractions, for larger fractions that have larger values in their denominators, but it's easy for linear factors. So let's look at, we need to split 7x plus 19 over x plus 1, x plus 5. Remember I said that we're going to just simply use letters, just the letter A over x plus 1 plus B over x plus 5. That's how we split. Then we are going to now evaluate the right hand side by trying to combine as if we're combining it back. As if we're combining it back by finding the LCM of the denominator. So we have A into x plus 5 plus B into x plus 1 over x plus 1 into x plus 5. Now, if we claim that the fraction on the left-hand side is equal to the fraction on the right-hand side, and as we can see, the denominators are equal, then it is only logical that our numerators will also be equivalent. So 7x plus 19 must be equivalent to a into x plus 5 plus b into x plus 1. Now, using the cover up method, we'll try to find each letter one after the other. We can start with A, we can start with B, but let's start with B. Now, if we're going to start with B, if we want to find B, we have to substitute a value that makes the A part 0. So the value that will make that A part 0 is minus 5, because minus 5 plus 5 is 0. So we want A to be out of the picture. So we're going to look for a value that will substitute into the whole equation that will make A 0. Okay? So that's minus 5. So let's put in minus 5. We have 7 into minus 5 plus 19 plus equals A into minus 5 plus 5 plus B into minus 5 plus 1. Like we said, minus 5 plus 5 is 0 now, so A becomes 0. So on the left hand side, we have minus 35 plus 19 equals to minus 4B. We got minus 4 from minus 5 plus 1, so minus 4B. So that becomes, minus 4B now equals minus 16. And then if we divide both sides by minus 4, we get B equals to 4. So that's the cover up method applied to find B now. Now to find A, think about it. To find A, we want to get rid of B. We want B to be 0. What should we substitute as a value for X for B to become 0? Think about it. What should we substitute as the value for X for B to become 0? Okay, simple. Check what B is beside B. We have X plus 1. So to make B 0, we need to put a minus 1 there. So to find A, we're going to put X as minus 1. We want B to be 0, so minus 1 plus 1 is what gives us 0. So we put X as minus 1. So by the time we do that, we have 7 into minus 1 plus 19 equivalent to A into minus 1 plus 5 plus B into minus 1 plus 1. Of course, B now becomes 0. So we have minus 7 plus 19 equals to 4A. So minus 1 plus 5 is 4, so 4A. So this becomes 4A equals 12. And then if we divide by 4, we get A equals 3. So you we got our answer as 3 and 4, which was our original values. Our original values at the beginning when we first started. So our partial fractions can now be written as, 7x plus 19 over x plus 1, x plus 5 equals 3 over x plus 1 plus 4 over x plus 5. So we've been able to split this using the cover-up method. Let me show you another method that you can use for solving partial fractions, which is called the comparing coefficients method. It's also easy and it's applicable for problems that have higher factors in the denominator. So we can use it here also. So we want to split the same thing. I'll give you all the different examples as we move on. So let's split 7x plus 19 now over x plus 1, x plus 5 using the cover-up method. Remember that when there are only linear values in the denominator, we assign just a letter A or B or C and so on and so forth. So we have now, we combine, we have A into x plus 5 plus B into x plus 1. Now, remember we said the denominators are equal, so the numerators must also be equal. Now, for comparing coefficients method, you're going to expand. You're going to open the brackets on the right-hand side. So we're going to have 7x plus 19 equals ax plus 5a. B into x plus 1 gives us bx plus b. So the next thing is to collect like terms. So we're going to collect ax and bx because they're terms in x. We're going to now collect 5a plus b. They do not have x, so collect them together. They are the constant terms. Now, we can now, put together the common terms. So we can have something like this. Ax plus bx will now become a plus b into x. And of course, 5a plus b remains as it is. Now we're going to compare. This is how we do the comparison. We compare the coefficients on the left to the coefficients on the right, and we obtain equations. So the coefficient for x on the left is 7. You know what coefficient means? The number beside x. So the coefficient of x on the left is 7, and the coefficient on the right for x is a plus b. Okay? So we have a plus b equals 7. That's the comparison there. We compare coefficients on the left with the coefficients on the right. Now, the constant term there is 19 on the left, and the constant terms on the right are 5a plus b. So 5a plus b equals 19. That's our second equation. So that's what we call comparing coefficients. Now, let's try to solve these two equations. They're simultaneous equations, so let's try to solve them. We can solve them by simply subtracting equation 1 from equation 2. So equation 2 minus equation 1 will give us 5a minus a will give us 4a, b will cancel out b, and 19 minus 7 gives us 12. So 4a is 12, divide both sides by 4, and a will be 3. Now if a is 3, we can take note that from equation 1, b is 7 minus a from equation 1. b, if we take a to the other side, b becomes 7 minus a. So b becomes 7 minus 3, which gives us 4 now. So we are back to the same answer. So regardless of whatever method you use, you should achieve the same answer. Whether you use the cover-up method or the comparing coefficient method. But take note that the cover-up method might prove difficult for some particular questions, and it will be easier and more realistic to use the comparing coefficients method. So here we have fraction now becomes 3 over x plus 1 plus 4 over x plus 5. So that's that for the non-repeated linear factors. Now, other non-repeated factors now that might not necessarily be linear, that they have, okay, denominators in the compound fraction, we have denominators that are not linear. How do we resolve into partial fractions now? So whenever you have a non-factorizable polynomial, that's a non-linear, and it's not linear, and it cannot be, if you have something that can be factorized, you can make it linear. We looked at one previously. But what if you can't factorize it, so it can't become linear, okay, and it has a degree n, in the denominator? You should assign a polynomial of the degree n minus 1 to the numerator. In the previous one, we said for the numerator, just use the letter a or b. But in this case, you need to apply a polynomial of the degree n minus 1 as the numerator. For example, if the degree is 2, that's if it's a quadratic equation in the denominator, your numerator should be a linear equation, a linear expression. Let me show you an example. So for example, we have something like this. 3x plus 2 over x plus 1 into x squared plus x plus 2. Now x squared plus x plus 2 cannot be factorized. So we're just going to, use a linear factor in the numerator. So let me show you what I'm talking about here. Let's resolve it. Let's resolve it now. So instead of just using a, okay, for the first factor, x plus 1 is linear, so we just assign a as the numerator. But the second one is not linear, it's a quadratic equation, so you would assign a linear equation to it. So that's going to be bx plus c. But let's assume the denominator was a cubic polynomial. You would then assign a quadratic quadratic expression as the numerator. Remember, degree n minus 1. The degree for the numerator is 1 less than the degree of the denominator. Okay? So 1 less than the degree of. So in this case, we have a quadratic denominator, so we have a linear numerator. So it's different from the previous one. So let's use the comparing coefficient method here. Let's see. So we have the combined, we have a into x squared plus x plus 2 plus bx plus c into x plus 1. Okay? Now, remember that numerators must be equal. So 3x plus 2 must be equal to a into x squared plus x plus 2 plus bx plus c into x plus 1. Now let's like what we said before for comparing coefficient method, we would expand the right hand side. So let's expand. So we should have a into x squared plus x plus 2 gives ax squared plus ax plus 2a. Then bx squared plus bx plus cx plus c. Now what's the next step here? The next step here is to combine the like terms, collect like terms together. So we have on the right side ax squared plus bx squared, then ax plus bx plus cx, then 2a plus c. Now let's try to group them. Now we have ax squared plus bx squared, a common term, so we say a plus b into x squared. Then ax plus bx plus cx, a common term, so we say a plus b plus c into x. And then we have 2a plus c. Now on the left hand side, we do not have terms in x squared, do we? We don't have any term in x squared on the left side. So automatically a plus b becomes 0 since there's no term, there's no coefficient of x squared on the left hand side. Now on the left hand side, our coefficient of x is 3. On the right hand side, our coefficient of x is a plus b plus c. So a plus b plus c is equal to 3. That's equation 3. Now on the left hand side, our constant term is 2. On the right hand side, our constant terms are 2a and c. So 2a plus c equals to 2. That is our third equation. Step by step, it's not difficult. Now let's simplify. If we substitute equation 1 into equation 2, remember that a plus b is 0. So if we put a plus b as 0 in equation 2, we have that 0 plus c is 3. So automatically c is 3. That's a simple one. We have c now as 3. So we can put c as 3 in equation 3 now. Okay? So if we do that, we have 2a plus 3 equals to 2. We take 3 to the other side, we have 2a equals to 2 minus 3, which is minus 1, and 2a is minus 1, so a will be minus 1 over 2. Minus 1 over 2, so that is a. Now, if we put a as minus 1 over 2 into equation 1 now, just take it step by step. If we put a as minus 1 over 2 into equation 1, we have minus 1 over 2 plus b equals 0. So our b, take minus 1 over 2 to the other side, our b becomes 1 over 2. So our a is minus half, our b is half, and our c is 3. Now our responsibility now is to substitute these values back into the original expression. So we have minus 1 over 2, that's a now, over x plus 1, plus 1 over 2x plus 3 over x squared plus x plus 2. So we can multiply, we can take the 2 for the first part of the expression, we can take that 2 down to the denominator, so it becomes minus 1 over 2 into x plus 1. Then we can, multiply the denominator and the numerator by 2 for the second expression. So if you multiply the denominator and numerator each by 2, we should have x plus 6 over 2 into x squared plus x plus 2. So that's our final answer for this particular example. Now, one thing about partial fractions is that resolving into partial fractions might be a bit long. Yeah, it can be very lengthy sometimes, but it's not difficult. If you understand the basic principles behind, this resolution, you can solve any partial fraction, no matter how long it is, and no matter how long it takes you to finish. If you just keep doing it step by step, you'll figure it out. So don't be taken aback by the length of the solution. Just purpose in your mind to do it step by step, and you get it. Okay? Let's take another example. So this one is a bit different. Now we have 3x squared plus 2x minus 1 over x squared plus 1 into 2x squared plus 3x plus 1. Now we don't have any linear factor in the denominator here. Our two factors here are quadratic. They are of the degree 2. So when we are going to be assigning numerators, we're going to assign numerators of the degree 1. That's a linear factor as a numerator. So this is how it's going to look like. Instead of just the letter A, we're going to say ax plus b Okay, and instead of just the letter C, we're going to say CX plus D for the second denominator. Okay, so we're going to also, combine the right hand side and see how it looks. So we're going to have AX plus B into 2x squared plus 3x plus 1 plus CX plus D into x squared plus 1. As usual, our numerators must be equal based on our premise that the fractions are equal. So our right hand side can be, before we equal the numerators, our right hand side can be expanded to get this. So ax plus b will be used to expand 2x squared plus 3x plus 1, and cx plus d will be used to multiply x squared plus 1. We should have 2a x cubed plus 3x squared plus x plus 2bx squared plus 3bx plus b plus cx cubed plus cx plus dx squared plus d. It's long, but you need to take it one step at a time. It's not difficult. You just do ax times 2x squared, then you do ax times 3x, then you do ax times 1, then you do b times 2x squared, then you do b times 3. It's not difficult. It's just long. I know some of us don't really like long. Anything that is long, you don't like it. But sometimes life itself is long. At least I think all of us are praying to live a long life. And it's you have to wake up every day and do something that every day. You have to keep doing something every day. It's a long life. So you just have to accept that, okay, some things are going to be long in mathematics, but if you really know what you're doing, it's not hard. It's not difficult, okay? So now we can write out our numerator for the right hand side like this and collect all the like terms together. The ones with x cubed together, the ones with x squared have been collected together, the ones with x have been collected together, and the constant terms b and d have also been collected together. So we can then, you know, group them based on their likeness. So 2a plus c into x cubed, 3a plus 2b plus d into x squared, a plus 3b plus c into x, and b plus d. Now, if we now compare these values to the equation, we know that on our left side, the 3x squared, that's 3x squared plus 2x minus 1, there is no coefficient of x cubed. So 2a plus c is going to be 0. But for the left hand side original equation, coefficient of x squared there is 3. You can go back to this equation here, you see this. Our coefficient of x squared here is 3. So it means that this 3a plus 2b plus d is going to be equal to 3. This is going to be equal to 3. Then for our left hand side, the coefficient of x here is 2. We're comparing coefficients. Coefficient of x squared, x here is 2. So everything here is going to be equal to 2. So a plus 3b plus c equals to 2. Then our constant term is minus 1 on the left side here, minus 1. So our constant terms here, b plus d is equal to minus 1. So yeah, it's long. We have 4 different equations, but let's see how we can manipulate these equations and, try to solve them. Now, from our equation, from our equation 1, we can see that c is minus 2a. Okay, if we take 2a to the other side from equation 1, c is minus 2a. Also, we can see from equation 4 that our d is minus 1 minus b. Okay, if we take b to the other side, we're just trying to manipulate here. If we take b to the other side, our d will be minus 1 minus b, right, in equation 4. Now, we have 2 new values. Let's now put these 2 new values as applicable into equations 2 and 3. So in equation 2, we're going to substitute d as minus 1 minus b, and in equation 3, we're going to substitute c as minus 2a. What is my end goal here? What is the end goal here? The end goal is we want to have just 2 unknowns in our equation. When we have just 2 unknowns, then we can solve them simultaneously, with maybe substitution or elimination method. So substitute these equations now into 2 and 3. We have 3a plus 2b equal minus 1 minus b equals 3. That gives us 3a plus b equals 4. How? 2b minus b is b, and 3 plus 1 now. If this minus 1 is taken to the other side, it becomes plus 1. So 3a plus b equals 4 now. Now let's do the same thing for equation equation 3 now. So we have a plus 2b minus a plus 3b minus 2a equals 2 now. This becomes minus a plus 3b equals to how? A minus 2a is minus a, right? So minus a plus 3b equals 2 now. So we can multiply. Now we want to solve 5 and 6. So but to get equation 6, let's multiply that a minus a plus 3b times equals to 2. Let's multiply it by 3. So we can have our a's common. So that will give us minus 3a plus 9. So we're going to multiply, take note, we're multiplying this equation by 3 to get this equation. So minus 3a plus 9b equals to 6. This is equation 6 and this is equation 5. So we're not going to substitute, solve this equation 5 and equation 6 simultaneously. We can use elimination method. So we're going to add 5 and 6 together. So 3a minus 3a will cancel out. B plus 9b will give us 10b and 4 plus 6 will give us 10. So if 10b equals 10, it means b equals 1, right? It means b equals 1. From there, we can now start finding other values. So let's try to get d. Since we know that d is minus 1 minus b, so minus 1 minus 1 is minus 2 for d, okay? Now we also know that 3a plus b, from equation 5 here, 3a plus b equals 4. So if b is 1 now, it means 3a plus 1 equals 4. So 3a, take 1 to the other side, 3a becomes, 4 minus 1 is 3, and 3a is 3, so so a becomes 1. You divide both sides by 3, a becomes 1. Same thing here, c is minus 2a. From equation 1, we derived that c is minus 2a here. So that means that if c is minus 2a, then 2a is 1. So c is just going to be minus 2. I hope you'll be able to understand what we are doing. It's long, but with, precision and, if you're gradual about it and you take it step by step, you get it. So A is 1, B is also 1, C is minus 2, and D is also minus 2, right? So our answer should look like this. So we're to resolve this. Now our answer should look like this. Since A is minus 1, A is 1, B is 1, so we have x plus 1. That's 1x plus 1 anyway, x plus 1. Plus C is minus 2, D is minus 2, so minus 2x minus 2. So that's our answer, but we can still work something out here. You can see that minus 2x minus 2, minus is common to both there, so we can bring out the minus and change this plus in the middle to minus. So we can bring out this minus, change this plus to minus, so we have something like this, x plus 1 over x squared plus 1 minus 2x plus 2 over x squared, 2x squared plus 3x plus 12. So that's our answer. Okay, so that's our answer for this question. Now let's quickly take a summary. We're not done with partial fractions. I don't want to overwhelm you. I know it's a bit long, so let's just take a calming breath, and in our next class we would talk about the remaining types of fractions that we could be asked to split. Now we talked about fractions that are non-repeated, that have non-repeated linear factors in the denominator, and we said we'll just use a single letter A, B, C for the numerator when we're splitting. And then we also said when it is non-repeated but it's not linear, you can't factorize it and you have non-linear values in the denominator, you use polynomials of the degree n minus 1 for the numerator. So if it's a quadratic polynomial, as the numerator, you should have a linear polynomial of the form ax plus b, for example, x plus 1, x plus 2. But in our case, since we don't know the value, we just say ax plus b or cx plus d, and so on and so forth. But if it's a cubic polynomial that's raised to the power of 3, we would use quadratic polynomial in the numerator. That's something like ax squared plus bx plus c. So you can just try to work out some of these questions and see what you can, derive on your own. See how you can solve on your own. Okay? So in our next class, we'll finish this up. So I want you to try to resolve these questions, these fractions, resolve them. Just try them. They are easy. They're easy. Remember that when it's linear, you use just a letter in the numerator, but when it's um, non-factorizable, you can use a polynomial of the degree n minus 1. Okay, so try to resolve these fractions and get back to me in the comment section if you were able to get it. And if you have any other thing you want us to explain further, you can also let me know. Okay, so I hope you have had a lovely class. Remember that if you want, you can try your best to like the video if it has been fun for you. You can also try to share to your friends if you think it will help them. And don't forget to subscribe and tell your friends to subscribe for weekly updates. And we'll be back again next week for another lovely class. So hope you're having a nice day. Remember to leave your comments in the comment section and take care of yourselves. Bye.